Right now, as you listen to this, the building you are sitting in is likely fighting this massive tug-of-war that you can't even see.
Oh, absolutely. It's happening right in the wall.
Yeah, and in one corner, you've got your beautifully sealed, brand new double-pane windows and weather-stripped doors. And in the other corner, you have the heavy machinery keeping your home warm.
Right, the heating system.
Exactly. And if those new windows actually win this hidden battle, the loser could quietly flood your living room with carbon monoxide.
Which is just a terrifying thought. I mean, it is a profound architectural conflict. We spend so much time, optimizing the aesthetic spaces of our homes, completely oblivious to the fact that a house operates very much like a living organism.
It really does. It has, complex respiratory system.
Yes. And when we alter the skin of that organism without understanding its lungs, well, the consequences become incredibly serious.
So true. Welcome to the deep dive, everyone. If you're joining us today, you are someone who loves to look under the hood of everyday life to understand the why behind the drywall.
The hidden mechanic.
Right. Today, we are unpacking a masterclass of a source document. It's this dense, highly technical engineering presentation, originally titled AS-TEMA04.pdf, that breaks down the fluid dynamics, safety standards, and structural designs of combustion product removal systems.
Which is a very clinical way of saying it's a survival guide to the hidden lungs of your house.
100%.
What is particularly compelling about this material is how it synthesizes international building codes. You see these strict European engineering standards bleeding seamlessly into Russian technical frameworks.
Right, because physics don't care about borders.
Exactly. It's a testament to the fact that the physics of combustion and the dangers of carbon monoxide are universal.
So our mission today is to translate this heavy engineering data into practical, mind-blowing realizations about how your own home works. And I see your visual backdrop today is this beautifully complex, layered schematic of a high-tech smart home.
I felt it was necessary.
It's absolutely perfect for the autopsy we're about to perform on modern housing.
Yeah, because to understand where modern buildings fail, we have to trace the evolutionary timeline of this technology. We have to start with how the earliest indoor gas appliances managed to breathe and how engineering has scrambled to adapt to our changing architecture.
Okay, let's unpack this. If we trace this back, the earliest, most primitive setup in the engineering classifications is what the industry calls Type A.
Type A.
And honestly, the best way I can visualize a Type A appliance is like someone doing intense cardio in a tiny closed closet.
Oh, wow.
Like the machines say a basic gas stove is inhaling oxygen from the exact same room it's sitting in, and then it just exhales all its raw combustion byproducts right back into that same airspace.
That is a very vivid analogy.
Yeah.
But let's refine it slightly.
Sure.
It's not just doing cardio in a closet. It's relying entirely on the flaws of that closet to survive.
Oh, I see what you mean. The drafts.
Right. In early housing architecture, rooms were notoriously drafty, wood shrunk, mortar cracked. The house naturally leaked enough fresh air that a Type A appliance could function without immediately suffocating the occupants.
But obviously, as construction got better, pumping raw exhaust into a kitchen became a huge health liability.
Unacceptable. Which forces the engineering evolution to Type B.
Right. This is where designers finally gave the machine a dedicated exhaust pipe. If you picture a classic gas water heater mounted on a utility room wall, that's usually a Type B.
Exactly.
It still breathes the room air, so it's inhaling oxygen from the hallway or the basement, but it exhales its toxic byproducts outside through a vertical chimney.
And that introduces a massive shift in building physics, because suddenly you aren't just burning air in a static room, you are physically vacuuming massive volumes of air from the inside of the house and throwing it outside.
You're creating a pressure differential.
A very complex pressure differential inside the living space, yes.
Right, and managing that pressure is what leads to the ultimate modern evolution, which is Type C. I like to call these the scuba divers.
Scuba divers, I like that.
Because a Type C boiler doesn't touch your room air at all. It features a completely closed combustion chamber. It pulls atmospheric air from outside the house through a dedicated intake pipe, combusts the gas inside its little sealed metal box, and then exhales through a separate exhaust pipe.
It is a completely self-contained, closed loop.
Exactly.
What's fascinating here is the sheer engineering paranoia required to make those Type C systems function safely indoors.
Paranoia is a good word for it.
The industry standard actually includes a very specific safety designation called the X index.
Okay, the X index.
When an appliance carries that index, it essentially signifies that the exhaust system is mathematically and physically foolproof against leaking hazardous gases backward into the living space.
So how do they actually achieve that foolproof status? Because it can't just be relying on like rubber gaskets and tight screws. Those degrade over time.
They absolutely do.
My understanding is they use active positive pressurization. They literally use internal mechanical fans to create an air pressure inside the exhaust pipe that is significantly higher than the atmospheric pressure of the room it sits in.
That is the core mechanism, yes. By positively pressurizing the exhaust flow, the engineers flipped the physics of a leak.
How so?
Well, if a microscopic crack ever developed in the exhaust pipe over time, the lower pressure air from your living room would actually push into the pipe. The toxic exhaust physically cannot push out into the living room.
Oh, wow. That is brilliant.
Right. Alternatively, the system uses the incoming stream of fresh air to continually purge the casing. The entire philosophy is active aerodynamic isolation.
And just to cover all our bases, the engineering timeline branches off into Type D as well, right?
Yes, Type D. Those are mechanical removal systems that use fans to force exhaust out without needing a traditional vertical chimney structure.
But really, the core question for you listening right now is to mentally walk into your utility room. Look at your boiler or your water heater. Are you sharing your indoor oxygen with a Type A or B, or do you have a Type C scuba diver hidden behind that metal casing?
It is the most critical question a homeowner can ask, because knowing exactly how your heating system inhales brings us directly to that invisible tug-of-war you mentioned at the start.
Exactly, because having a Type B appliance, the one that exhales outside but still breathes the air in your house, has suddenly become incredibly dangerous in modern, newly renovated homes.
It is a crisis entirely of our own making, and it is driven by the sheer ravenous math of combustion. We don't generally think of fire as having a diet, so to speak.
Right, a diet.
But sustaining a safe chemical reaction requires a staggering volume of oxygen.
The numbers on this actually blew my mind. The source states that for every 1 kilowatt of nominal thermal power, a gas appliance requires 4 cubic meters of supply air.
That is a lot of air.
It's wild. So if you have a standard 24 kilowatt boiler heating your home, that machine needs to inhale almost 100 cubic meters of fresh air every single hour just to run safely.
That is the entire volume of a large living room.
Sucked through the boiler and pushed out the roof every single hour.
And historically, this just wasn't an issue. Older homes accommodated this massive air exchange because they were essentially giant architectural sieves. The house provided a constant, if inefficient, stream of fresh air for the boiler to consume.
But here is where we completely sabotage ourselves.
Oh, yeah.
Let's say I have that powerful Type B boiler in my basement, but I just spent $20,000 on brand new, highly insulated, double-glazed windows. I weather stripped the heavy exterior
You
doors.
seal the envelope.
Exactly. I effectively wrapped the entire house in a tight plastic bag to save on my winter heating bills. So when that boiler kicks on, it tries to violently inhale 100 cubic meters of air, but the room is locked down. It's practically a vacuum.
Precisely. You've choked off the supply. And it is not just the passive sealing of the house that creates the danger.
Right.
We actively install mechanical enemies. If someone is taking a hot shower and running a bathroom exhaust fan, or cooking and running a high-powered range hood, those fans are aggressively ejecting air from the house.
Right, so they are in a literal tug-of-war with the boiler for whatever tiny scrap of oxygen is left in that sealed house.
And the boiler is just relying on the passive, natural upward draft of a hot chimney, while the kitchen hood has a high-speed electric motor.
The kitchen hood is going to win that fight every single time.
It will. And when the boiler loses that tug-of-war, it begins to suffocate.
Yeah.
This is where the physics turn deadly.
Yeah.
When natural gas burns with abundant, freely flowing oxygen, the chemical reaction is clean. The primary byproducts are relatively harmless, just carbon dioxide and water vapor.
But when you starve that flame of oxygen, the chemical reaction fractures. You trigger incomplete combustion.
Yeah.
Instead of producing CO2, the fire starts stripping oxygen atoms away, and it produces carbon monoxide, odorless, colorless, and highly lethal.
If we connect this to the bigger picture, it reveals a fascinating, yet incredibly dangerous paradox in modern building science.
This is...
The massive global push for energy efficiency, sealing our homes tightly to lower carbon footprints and save money, is fundamentally incompatible with older, room-breathing heating technologies.
Wow.
We fixed the drafts, but we accidentally choked the lungs of the building.
It's the ultimate unintended consequence.
Okay.
So we've established how the machine inhales and how our modern renovations are starving it of air. Now we need to look at how it exhales.
The exhaust side.
Right. If the boiler actually manages to get enough air to burn, where does that exhaust go? Because I was genuinely shocked to learn that a badly constructed chimney can take a state-of-the-art, hyper-efficient boiler and utterly destroy its performance.
Oh, entirely?
Like dropping its efficiency from 95% down to a dismal 60%.
It seems highly counterintuitive. I mean,
Yeah.
a chimney is just a hollow tube. How could it possibly drain 35% of a boiler's efficiency?
Exactly.
But it all comes down to the complex thermodynamics of the exhaust plume, and specifically, the concept of the dew point.
Right. For anyone who hasn't thought out thermodynamics lately, the dew point is essentially the temperature threshold where invisible water vapor cools down enough to suddenly condense back into liquid water droplets.
Yes.
And because the chemistry of burning natural gas, which is a hydrocarbon, involves hydrogen atoms bonding with oxygen, it creates a massive amount of H2O.
People forget that.
Boiler exhaust isn't just hot air, it is incredibly humid, wet steam.
Exactly. As that hot, wet steam travels up the vertical column of the chimney, it transfers heat into the walls of the chimney. If those walls are too cold, the exhaust temperature drops below the dew point, and it literally starts raining inside the chimney.
Raining inside the house.
Yes. This sets up a profound architectural showdown between traditional brick chimneys and modern metal flues.
Here's where it gets really interesting. Because traditional brick chimneys are the absolute worst-case scenario for a modern boiler.
They are the loser in this showdown.
Big time. First, just structurally, they are usually rectangular, which creates terrible aerodynamic drag in the corners. But the real killer is their thermal mass.
The sheer weight of them.
Right. A thick masonry chimney is essentially a giant heat sink. It takes a massive amount of energy and roughly 35 to 45 minutes of constant boiler operation just to heat those bricks up past the dew point.
And during those 45 minutes, your chimney is stuck operating what engineers call a wet regime. And we need to be clear here, it isn't just pure, clean, distilled water condensing on those bricks.
No, not at all. It's a highly corrosive cocktail. The exhaust contains sulfur and nitrogen compounds from the gas.
Exactly.
So when that water vapor condenses on the freezing brick, it mixes with those compounds and creates sulfuric and nitric acid. The chimney is quite literally sweating a weak acid.
Sweating acid, that's exactly what's happening.
And because brick and mortar are highly porous materials, they absorb this acidic sweat like a sponge.
It is a devastating chemical attack from the inside out. Over a few harsh winters, that acid dissolves the mortar joints. It migrates horizontally through the masonry, eventually leaching through the plaster on the interior walls of your home.
Causing massive structural and cosmetic decay.
Exactly. Meanwhile, a modern insulated stainless steel tube behaves entirely differently.
The winner of the showdown.
Yes, because thin metal has very little thermal mass, and it's surrounded by insulation. The hot exhaust flashes the metal past the dew point in just 1 or 2 minutes.
So it achieves a safe, dry regime almost instantly.
Not to mention the metal is completely impermeable, so it doesn't absorb the acid even when it does condense. And its perfectly circular cross-section allows the exhaust gases to maintain high velocity, escaping into the atmosphere before they have a chance to cool down.
This perfectly explains why throwing a brand new, high-efficiency boiler onto an old brick chimney is such a disaster.
It really is.
Because high-efficiency boilers are efficient, specifically because they extract almost all the thermal energy out of the combustion process to warm the water in your house.
Right, they keep the heat inside.
That means their exhaust gases are incredibly cool right out of the gate. They literally never get hot enough to warm up a massive brick structure.
Never.
So the chimney just rains acid inside your walls perpetually, killing your heating efficiency and destroying your masonry.
It is a complete mismatch of generations of technology.
So if brick chimneys are structurally out and retrofitting a towering metal tube up through 5 floors of a historic brick building is a logistical and financial nightmare.
A total nightmare.
You might look at the architecture and think, well, why go all the way up the roof at all? Why not just punch a hole straight through the exterior wall and vent the exhaust out the side of the building?
Ah, facade venting.
Yeah.
It is incredibly tempting, and as the technical material outlines, it is technically permissible under certain very narrow legacy regulations for residential buildings up to 10 stories.
10 stories, okay.
But what is technically allowed on paper and what is practically advisable in engineering are two wildly different things.
Yeah, the engineering consensus here is that facade venting is an absolute disaster waiting to happen. It's the illusion of a quick fix.
A very dangerous illusion.
If you just blast this stuff horizontally out the facade, you are taking that exact same acidic water vapor we just talked about and spraying it directly onto the exterior of your building.
Yep.
Over a single winter, it just eats away the stucco, peels the paint, and degrades the structural masonry right around the vent.
And it creates an even more immediate, catastrophic mechanical failure in dead of winter. Think back to those Type C scuba diver boilers.
The closed-loop ones.
Right. They have an intake pipe for fresh air and an exhaust pipe for the hot gases. If you route both of those pipes straight out the wall right next to each other, you create a fatal freeze loop.
Because the intake pipe is aggressively sucking in sub-zero freezing air, while the exhaust pipe mere inches away is blowing out wet, humid steam. The freezing air instantly flashes that steam into ice.
Precisely. The condensation forms directly inside the air intake as the steam is drawn backward by the draft, or the ice builds up externally like a glacier over the fan.
Oh, man.
Within hours, the intake chokes itself off completely. The boiler's internal airflow sensors detect a pressure failure, and the entire system abruptly shuts down.
Leaving you without heat on the coldest, most brutal night of the year.
Exactly.
And even if it doesn't freeze, you are pumping concentrated carbon monoxide and nitrogen oxides directly into whatever cross breeze might carry it right into your neighbor's open window.
It's just a complete failure of design.
So what does this all mean? How do modern engineers actually solve this respiratory crisis for the building? We can't use the old brick, going up the roof is too hard, and we can't go out the side.
They solve it through a masterpiece of fluid dynamics and thermal engineering known as the LAS, which, going back to your point about international standards bleeding together, stands for Luft-Abgas-System.
A German term acting as the gold standard in a Russian engineering document.
Exactly. The air and combustion product system. It sounds highly technical, but the core mechanics are actually stunningly elegant once you math them out.
It's the ultimate evolution of the closed loop, right?
Yes. The most common and effective implementation of an LAS is a coaxial system. Imagine a pipe suspended perfectly inside a slightly larger pipe.
Like a tunnel running directly through the center of a larger tunnel.
Exactly right. The inner pipe is dedicated solely to pushing the hot, toxic exhaust gases out of the building. The outer ring, so the negative space between the inner tube and the outer casing, is dedicated to pulling the fresh, cold atmospheric air down into the boiler.
Which is so brilliant because they're exploiting the laws of thermodynamics instead of fighting them.
Right.
As the scorching hot exhaust travels up the inner pipe, it naturally radiates heat outward. But instead of that heat being lost to a cold brick wall, it's absorbed by the freezing cold winter air rushing down the outer pipe.
Yes.
The exhaust is literally preheating the boiler's incoming air supply before it even reaches the combustion chamber.
That preheating action serves as a highly efficient built-in heat exchanger. The boiler no longer has to waste expensive natural gas heating up sub-zero air. The air arrives pre-warmed by the waste heat of the exhaust.
That's incredible.
And simultaneously, that cold incoming air acts as a constant insulating jacket, drastically cooling the outer skin of the entire pipe system.
Which makes it vastly safer to run through the internal structure of a multi-story building. You don't have a blazing hot pipe pressed up against wooden floor joists.
Exactly.
And the engineering safety tolerances on these LAS structures are wild. Because they often serve as a central collective artery running up through multiple units of an apartment block, they are engineered to be virtually indestructible.
They absolutely have to be. If a fire breaks out in a first-floor apartment, the central chimney cannot become a vertical highway for fire and toxic smoke to rapidly reach the penthouses.
That would be catastrophic.
It would. The technical standards dictate that these coaxial systems must maintain a rigorous 90-minute fire resistance rating for high-rises.
Meaning they can be completely engulfed in a direct, raging fire for an hour and a half without their structural integrity failing or the fire breaching the inner compartments to spread upward.
Correct, or 30 minutes in lower residential buildings. It isolates the hazard completely. By adopting the LAS, the entire building effectively transitions to that foolproof Type C methodology.
The mechanical lungs of the building are hermetically sealed off from the living spaces where humans breathe.
Exactly.
This has been a truly fascinating progression to trace today. We started by looking at how these machines evolved to breathe from the primitive Type A appliances doing cardio in a drafty closet to the fully isolated Type C scuba divers.
A huge leap in engineering.
We unpacked the dangerous paradox of how our modern, perfectly weather-stripped renovations are literally suffocating older boilers in a vicious tug-of-war for oxygen. We witnessed the architectural showdown between old brick heat sinks sweating acid and modern metal flues.
Right.
And finally, we arrived at the brilliant coaxial heat-exchanging design of the LAS systems.
It completely shifts how you view the infrastructure hidden behind the drywall. And this raises an important question.
I'm ready for it.
Think about the building you are sitting in right now as a living organism. You've likely upgraded its skin over the years with tighter insulation, heavy doors, and new windows to keep the cold out and lower your bills.
Right, optimizing the skin.
But in optimizing the skin, have you accidentally suffocated its internal organs? Next time you hear your heating system click on in the dead of winter, ask yourself, where exactly is it taking its next breath from?
That is a haunting but entirely necessary thought to leave on. Thank you to everyone listening for joining this deep dive. We love taking these incredibly dense engineering manuals and finding the high-stakes stories hidden inside the blueprints.
It's been great.
We praise your curiosity for taking the time to learn something genuinely complex and vitally important today. Until next time, keep looking under the hood.